Bismillahirrahmanirrahim. Assalamu alaikum. Today we will study about the jump, loop, and call instructions for 8051 microcontroller. And chapter 3 is the Mazidis book related to this topic. The main learning outcomes are we will know about these three basic the instructions, jump, loop, and call instructions. And we will use Keil for testing the code and Proteus for testing the hardware as well as the assembly code. So there will be some good demos. What is loop instruction? Basically, the loop instruction is when we are going to repeat a specific some kind of instructions a certain number of times. So in programming language, this is called a loop. In assembly language, actually, we are going to use some internal registers of the CPU for looping instructions. So let's see how we are going to do this. So first instruction is DJNZ. DJNZ is the instruction that means decrement the register. There is a specific register here, and then see if the register is equals to 0. In case register is equals to 0, don't jump to the label. And in other words, if the register is not 0, jump to the target address mentioned as label. The syntax is like this: DJ jump decrement. Okay, so inherently in this we are going to use actually a register. So D decrement and jump if not 0. So there is a register that we are going to decrement this register, and when you decrement this register, reduce it with 1 and see if the register content is 0 or not, and then we will go and jump to this label. This label basically refers to this will refer to memory location, okay, where your code is. This is an example. For example, add 3 to accumulator 10 times. So there is something, addition is an operation that we have to do it routinely. So let's see how this can be written in the program. ORG 0, this is the, when we restart the 8051 microcontroller, so it will be pointing at this address. So we are putting our code here. So move A0, initially we put A, content will be all zeros. Okay, this will be 0, 8 bits. And I have written 2 zeros as hexadecimal. And then we load in R2 the value 10. This 10 is basically the counter, and R2 is we are trying to use R2 as a counter for this program. Okay, we can use any other registers as well. And then we give a label to this place. Let's say label 1, and here is the instruction: add a hash 03. So this will add 3 to the accumulator. So 3 will be added here, and the answer will be let's say 03 here. Okay. Okay, and then this is the time that we have done it. One time addition is done. So one time I added. So what we need is the R2, the counter R2, which contains the value 10, needs to be subtracted decrement. So we have a very powerful instruction, which is decrement and jump not 0. So decrement will first reduce R2 from it will do R2 is 10, it will subtract 1, and the R2 will become 9. And then it will check again if, so we have R2 minus 1, then it will check that if R2 equals to 0 or not. Since R2 is not equals to 0, so it will jump to the location. So label 1, and label 1 is where it is here. So it will jump again here, and it will keep doing this thing, that is add 3 to accumulator. As far as this R2 will be, the next time it will be 8, and finally it will become 0. So when the R2 becomes 0 after 10 loops, it will not jump to this level, but it will move on to the next instruction. So the next instruction, if you see here, is the next instruction we have here is move. We are moving the sum into the register R5. Okay, so the sum is placed in the register R5. Okay, so this is how the loop instructions are used. Let me go and show you example in the Keil software. So this is a demo here, and let me make it 0 because I put many uh, examples, all examples in the sequence. And what I'm doing here is I put org 0 to make sure that which instruction example I want to. So now this is the example number 1. Focus here, and so on the screen now you see the example number 1. Example number 1 is about adding the 3 accumulator 10 times. This is Keil software. Now I'm going to build this, and once it is okay, no error. Now I will go and test the debugger. Here it is now. Right. So you see it is pointing to the first instruction. So we will step in. You can see the registers R0, R1, R2, R3, R4. The registers that we are caring about is A. A is here, 0. R2, currently R2 has nothing here. So when I step in, you will see the R2 will get 10. Okay. See the R2 gets 10. Okay, now tell me what is the difference between, I tried to move 10 here, but in R2, I got A. Okay, so later on, I will ask this question. So keep in mind and have a good answer about it. I will continue. So I will continue with this. And the next instruction is add 3. So the 3 will be added in register A. So it is 3 available. And now we are here in this command. It will check R2. And you will observe that R2, whatever the A value is, it will be decremented 1 value. So you see it is decremented. Actually, it was in hexadecimal. This displacement is in this displays in hexadecimal. So in hexadecimal after 9, it is not 10, it is A. So that was A. Here you can see the A given in decimals. Okay, and if you click here, it is also showing that this decimal A is basically 0A. This decimal 10 is basically 0A. Okay, I will step in again, and it will keep this time adding 3 to 3 is 6. Next, it will become, and 1 is decremented here, and it becomes 9. And here I will get R2 will become 7, and I will keep doing it. And you see it is going, the program comes here, and then it checks and goes back to this memory location label 1 until we have 2, and then now we have 1. So what will happen now? Now when I will run this example, okay, this time it will decrement and move forward to this 22. You see now it is moved to 22, and R5, you can see R5 is right now 0, and A contains 1E. So now 1E will come to R5. Here it comes. Okay, so this is a simple demo for, okay, now continue with this. So this is a snap of the program that I just showed you. So what we did, actually, this is the example from the book, example 3.1. I just put a snap here. So prior to start the loop, a register R2 was chosen, and we loaded it with the counter value 10. And we should note that we can use any register from R0 to R7, or even some RAM location as a counter. Basically, this works like just a soft counter, and it's a value that we are manually or by programming, we are actually, through this programming, actually we are reducing. Now the question is, in case of an 8-bit register used as counter like R2, okay, so you have an 8-bit register, okay, and this, which is what we are using as a counter. What do you think you can repeat the loop? In other words, what I'm asking is the maximum number of times that we can repeat this addition of 3. Okay, so keep in mind this question. I may ask you few, I will show you such questions for the quizzes or other exams. Next comes the nested loop. Nested loop is what? For example, whatever the counter you use, it will have some kind of a limit, a maximum number. For example, for 4-bit counter, the maximum count you can get is 16. For an 8-bit counter, you can get maximum of 256. Okay. So in case if we need to increase for example, you need to repeat something 500 times. Okay. So how you are going to do this? Because your counter will saturate after 256 counts. So for that one, what we do is we actually nest. We nest in the main loop some other loops. So this is called nesting loops, nested loops. So we can use multiple register for that purpose, and which coordinate and hold the count. So this is an example of the nested loop. We need to write a program that load the accumulator with the value, okay, 55H, and complement the accumulator 500 times. You see, it is exceeding. So this is an example of the program that it can do. What we are doing here is move A 55H. So we place 55H in A, very good, no problem. And then we move, because 700 means I can divide it like this in 2 registers. So one register will take care about, for example, 10. If I run a loop 10 times, okay. And within this loop, if I run it for, let's say, 70 times. So 10 times 70 will become 700 times. So this is what we have done here. So we actually put 2 loops here, and these are the labels: example 2, label 1, example 2, label 2. And this is an inner loop. It will run for 70 times. Okay. And this will run for, the outer loop will run for, let's say, 10 times. And they together will make the count 700 times. Okay. Now you see what's happening here. We use two counters. R3 is the outer counter, R3, and then inner counter is R2. R2 contains 70 and R3 contains 10. And we are actually complementing A here. And this is how the loop is going to continue. So we jump to this point. We jump to this point 70 times. This is 70, okay? And once we are done, and this 70, so R2 will be 70 for the first time, then it will be 69 and so on, okay? And the same thing goes for R3. R3 will be 10 and ultimately it will go to, so it will be initially outer loop will be 10, 9, 8, up to 1. Okay, so the overall, this is a one program that is showing how the nested loop will help. Let's do it in a simple example, because 700 times is difficult. So I prepare a small count example of, let's say, 35 times, and it can be done with the 1. But what I'm trying to show you how the loops are working. So I put intentionally 5 here for R3 and 7 here for R2. So basically it makes like 35 times. Okay. So let's go to the software. Now, let me stop it. Okay. Right. And I will make a small trick here. So I comment this one, it will come there somewhere, and I will, okay, so remove this 2, and even not here, this one, okay, the small one. So now when I compile the code, you will see my code will take this, all these instructions will be forced to be at this location. So the program counter will come directly here, right here. So this is in the memory location from 0. And okay, so in A, there is nothing. 55 will go here. Let me step in. So 55 is here. And we are here on R3. R3 is currently 0. R3 will take 5 now. Then this is label 1. Then I will move further. Complement A. Now comes the DJ NZ. Okay. Okay. So now next, you see R2 is decremented one time. Second time, you see it is not moving beyond this instruction. It is continuously working for the inner loop till I will have R2, focus on the R2. It was 7, then 6, 5, 4, 3, 2, okay, and now 1, and this time it will move to the next instruction. Okay, now we are in the R3. R3 contains 5. So it will decrement, it will become 4, and you will see it will jump to, since 4 is not 0, so it will jump to the first label. You see, now it moves back to the outer loop and coming here. Now again, the inner loop is working, okay, till R2 gets back to 0. Now it will jump to the outer loop, and outer loop we reset R2 with it. Currently R2 is 0. We reset it with the 7 for the inner loop. It goes 7. Okay, the inner loop works and then goes for the outer loop, and it continues until we will have R3. You see R3 is 2, and finally R3 will now it will move to the next instruction. Okay. Okay, now continue with the lecture. So this was the nested example. Another interesting is the conditional jump, JZ. JZ is jump only if a certain condition is met. And this, its syntax is JZ and the label. It inherently uses A register. So jump if A is 0, although A is not here, you cannot see A here, but inherently it is used in this case. And therefore this instruction must be used with the A in mind. You cannot use this instruction without the involvement of A. So even if you have some value in other registers, for example, here in the example, determine if R5 contains the value 0. If so, put 55 in it. So if we decide to use this JNZ or JZ instruction, we have to involve R5, involve A, and put R5 in A here. And then we say jump if not 0. It means jump if A is not 0. In other words, what you're saying here is jump if R5 is not 0, okay, via A register, okay. So, okay, so move R5 55, and if so, it will move next to it. Conditional jump, JNZ refers to the jump if no carry is generated in calculation. And this is actually C, not this is C. Okay, JNC. Okay, this is a little mistake, so please make it C. So this is this inherently works for the carry flag. So the syntax is quite simple, but inherently what happens behind is it goes and checks the carry flag, and it helps us in the different calculations. So if carry flag is 0, the CPU will start fetching and executing the instructions from the address of the label. If carry flag is 1, the CPU will not jump to the label. Instead, it will move to the next instruction below this statement. And so this is an interesting example of JNC, in which we have to find the sum of 79. So 79 is in hexadecimal. It means we have 0, 1, 1, 1, and 9 means 1, 0, 0, 1. And F5 is basically all ones here, and 5 is 0, 1, 0, 1. And E2 means we have 1, 1, 1, 0 and 0, 0, 1, 0. So how we are going to do this? If we add any of these two, it will be very interesting. So let's do it, and the program will go like this. Okay, I will place this into register number A, and then I will add to it. So this will come here. 79 will come here, and we will add F5. And what we are going to do is, after this addition, we are going to check the outcome. Okay, so check if carry flag carry flag is generated. Okay, in case if the carry flag is generated, we will save the carry flag. Okay, CY, let's say, into some register, let's say R, I'm not sure, R5, yeah, R5, because R5 is taking care of the high byte. So high byte is the place where the carry will go. So R5, we will move it to the R5 register. And then next, we will have whatever the accumulation will be, it will be in A register, right? And then in this, we will take and add this value of E2, E2H. And then again, we will check if carry flag is 1. If yes, then we will increment or increment R5. Okay, or add this carry flag to the R5 register. Okay, so this is how it is going to do. Because if you see here, roughly if I calculate 0, 1, 1, 1, and 1, 0, 0, 1, this is 79. And F5 will be, this is an A, okay? And F5 will be 1, 0, 1, 0, and then 1, 1, 1, 1. So if I add these two, what I'm going to get is, I'm going to get 1, 1 goes 0 and 1, then 1 come here, then 1 here, then 1, 1 will go 0 and 1. This time 1 and 1 goes 1, 0, and 1, 0 added with 1 will be, so 1, 1 add to 1, 0, 1 added to this one will become 1, 1. So I'm going to get 1 here, carry 1 here. The 3 ones will 1 and 1. The 2 ones will generate 0, and then 1 will be, because the 8 bits are done. So the 1 will be, the 1 generated will go to the carry flag in the program status word. Okay, so CY is set. It means CY is equals to 1 here. Okay, and then okay, so we will keep this there, and I will take this one because this is an A, 0, 1, 1, 0, and 1, 1, 1, 0. And then start adding this E2. E2 will be 0, 1, 0, 1, 0, 0, and then this will be 0, 1, 1, 1. This is over E2H. Let me do this, and then I will show you the program. 1, 1 goes 0, 1, 1, 1 goes 0, 1, 1, 1 goes 0, 1, comes here, 1, 1, 0, 1, and this time we have 1 here, 1 here, 1, 1 goes 0 and 1 again. So 1 is generated as a carry flag CY is equals to 1. Now this will override this one. So going back here, so once we had in any calculation, if I have the carry flag, I should save it to R5. So it should be moved to R5. And the next, this carry flag means this is the 13 bit. So this bit should be added to R5. So this should go and add to R5 plus 1. And it will be, because we already had in R5, we already have 1, 0, 0, 0, 0, 0, 0, 0, and this one will come here and add it to it. So we will get 0, 1, 0, 0, 0, 0, 0, 0. So our answer will be, because the low byte are 0, so A will be placed in R0, and R5 is already having the high byte. So we have this is the low byte, and we will have this in the high byte. Okay, now I will show you the program. is the program, and I will show you now. So in this example, we just did it again. So we needed to do the sum of these three numbers, right? And so we started with moving 0 into A, okay? And then R5, we clear R5 as well. A is loaded with 79. And then we added 0F5, okay? This gives us 6E, and a carry flag is generated. And then we are jumping to then this next label if carry flag is not generated, okay? So jump if carry flag is not generated, we will directly come here, but a carry flag is generated. So carry flag is generated, we need to save it. So we come here and save the carry flag in R5. And this is how we are doing, because incrementing R5 was 0. So incrementing R5 is making it R5 will be getting 1 here, carry flag. Now, this is the third number, okay, E2. E2 is added to A5, and the result will be 50. Okay, if you see here, this number was 50. Okay, we added this. This is 5, and this is 0. So 50 is generated, and a carry flag is also generated. So again, the carry flag is generated, so we need to increment and save it. Otherwise, if there is no, we have to jump it. So we are jumping only in case there is no carry flag. So the jump is only where jumping only when carry flag cy equals to 0. Otherwise, if carry flag is 1, we must um, add 1 to higher bit, okay, or higher byte, which is taken care by R5 here. Okay, so increment is done here, and finally the lower R5 is already having the high byte, and the low byte is in A. It will be placed in the R0. Okay, so let me show you in the Keil software. The code is already here. I just need to do one thing. First, I will stop the debugger. Okay, and putting a comma here. Yes. This is example number 3, right? Okay, so I will, yeah. So I will recompile so that this is placed in the properly at the right place. Now we will run it, and our code should be, yeah, our code is at this point. So let's start now, and now keep observing the values. Add A contains 0 right now, but now it will get 79. It's 79 now, and then we are adding 0F, and you can see the program, the status word. The last one is the carry byte, and okay, so these are all the registers. And let's continue. These are the system registers. These are values here. Let me expand it a little bit. Yeah. So and finally, you see, we have this value here. Okay. So other jump instructions in 8051 include, for example, these are all the other instructions we have. Quickly, specific to A, for example, jump. If A is 0 or not 0, we have 2 instructions for that. Compare and jump is these instructions. Okay, we are comparing and jumping. Check carry flag in the program status word, and then jump. Okay, jump. So these are the taking care of this carry flag. And then we have directly we can put some bits. Okay, jump directly if the bit is 1 or 0, and also we can clear the bit as well. So these are the quite strong instructions. Now, just before concluding this, I will show you a Proteus example. Before that, this can be an example of a situation. For example, in O1, we are having some input from the O1 is connected, and we are having some input at, let's say, P2.3, and if goes high, the O1, it means the temperature is very like high, and we are actually monitoring that bit, and we have to do something about it, like buzzer on some other port. So this can be a jump can do this job interestingly. So keep monitoring for this. So it will keep monitoring jump, not bit. So jump, keep bitting, keep jumping here, keep jumping. So it will keep jumping here until your P 0.3 is equals to 0. Okay, so if not bit, okay, if not bit means it will keep jumping, and the moment it is when we will have a P 2.3 equals to 1, it will move forward. It will move to next instruction, and the next instruction is set bit P10. This may be an alarm. Okay, and then you can make it high or low. So this is an example now. I prepare one example in Proteus. Quite simple. We have, let's say, one light connected to P2.6, okay, P2.7. It may be an alarm or a light, okay, light or a LED, okay. And we have P1.0 is, let's say, connected with the oven, okay, for example, oven. And here I'm simulating with the, instead of a sensor, I'm using a push button, okay, push button to show you how it will work. And there is a command here, program here. So I will now go and show you in the Proteus, the code I think was here also. Yeah, so this is a small, this portion is showing the code, very small code, org0h, move A0, okay, it's clear. And then this is the loop testing, it will keep jumping, okay, move P0. So this will set bit, sorry, this is the, I'm setting bit 2.7 equals to 1 high, and then I move A to the port I'm moving here. It's only for some testing purpose. Actually, what I'm doing here is jump, not J and B, P1.0, this point, this port to the test. Okay, so I'm jumping here. And once I will push this, it will move forward and it will clear 2.0. So let's do the, okay, so this is, here is the source code. Okay, this is the source code that I showed you. And now I will run the simulation. Okay, now it's running. And you see, whatever the logic is, this is with the pull-up resistor, it is high, okay? And this is currently 0. So when I press here, you will see it is currently glowing. So it will, so it may be a green light and then it will turn off. Okay, just to show you, okay, it may be the other way around. Okay, so this is the Proteus example, and I will, so we will conclude on the, so still we have few more remaining. So I will conclude from, we will start from the next lecture from here onwards. Okay, thank you very much.